most of our review focused on what we're going to talk about today, so that means we don't have to lecture for as long. But does anybody have any questions about what we talked about, real gases and the van der Waals equation? Just to give you guys a heads up on that. The exam is not meant to test your algebra skills, although that is a prerequisite for this class, and it is something that you should be able to do. If I do give you this question that requires you to use this on the test, I won't ask you to solve for moles, since that's appearing in more than one place. It's way more difficult to solve for mathematically. I would probably only ask you to solve for temperature or pressure. That only appears once, so you should be able to rearrange the formula and solve for either temperature or pressure. It would probably be in the context of a question similar to this, where if I'm asking you if a gas is behaving ideally, well, the way to determine if it's behaving ideally is to use the ideal gas law to measure its properties or property, and then use the van der Waals equation to measure its property and see if they match. Right? If the answer you get for pressure or temperature using this equation is the same as what you got using the ideal gas law, then it should be behaving ideally. All right, so quantitatively, you should be able to solve that equation for pressure or temperature using some algebra and plugging in all the other variables and all the other given information. Qualitatively, you should also know the difference between a real gas and an ideal gas has to do with the intermolecular attraction. Right? So to behave perfectly ideally, there won't be any intermolecular attraction, and that will be present at a high temperature with a large volume and a small number of moles. So the opposite conditions would be the conditions that you would create the most deviation from ideal behavior. So in 11.7, talk about mixtures of gases, and this is obviously excellent. Most gases are not like necessarily one pure substance. Like the air around us is a mixture of a variety of different substances. Excuse me. So when you have a mixture of gas, actually it's pretty straightforward. Because most gases behave ideally, we're going to assume ideal behavior for most situations. If I have 100 molecules of oxygen, and they're all bouncing around, that's going to cause the same pressure as if I had 50 molecules of oxygen and 50 molecules of nitrogen, because no matter what the substance is, if it's behaving ideally, there aren't any intermolecular attractions. It doesn't matter how heavy the molecules are, right? Because if it's all at one temperature, the heavier molecules are moving slower, so that they have the same average kinetic energy as the faster molecules that have less mass. So the identity of the particles doesn't matter. What matters is how many of them there are. So when you have a mixture of gases, if you have a certain number of moles of nitrogen under certain conditions, you can plug that in to figure out what the pressure resulting from those moles of nitrogen is. And if you have a certain number of moles of oxygen, you can plug that in to figure out what the pressure would be resulting from the oxygen. So what would the pressure be if I had 2 moles of nitrogen under these temperature and volume conditions? Yeah, so if I have 1 mole of nitrogen at this temperature and this volume, 1 mole requires or produces a pressure of 4.48 atmospheres. So if I had 2 moles, it would be double the pressure, assuming that the temperature and the volume aren't changing. So 2 moles would be 8.96 atmospheres. And so if I had 2 moles of pure nitrogen, that's going to be the pressure. But if I have 1 mole of nitrogen and 1 mole of oxygen, I still get the same situation, right? So the pressures are additive in a mixture. That's the bottom line when we're talking about mixtures of gases. If we want to know the total pressure, we can find these partial pressures, or the pressure resulting just from one of the substances present and added to the pressure resulting from the other substances present, and that gives me the total pressure. Another way to set that up, which is probably easier, would just be to say if all I want is the total pressure, that's going to be equal to the total moles times RT over V. So if I know I've got 2 total moles, doesn't really matter what the substances are. If all I want is the total pressure, I just add the total moles together and plug that in. Then I plug in the volume and the temperature and the value for R, and I would get the 8.96 atmospheres for that mixture of gases. So it's pretty straightforward, and then it's just a visual description of what we just said. The total pressure for a mixture of gases is equal to the individual pressures of the individual gases added together, the sum of them, right? So this big Greek sigma symbol means I'm adding, or it's the sum of those individual pressures, right? So conceptually, if I have a few molecules of one gas, that creates a certain amount of pressure due to the collisions that gas exerts on the inside of the container. A few molecules of a different gas creates its own pressure. And so if I have all those in the same container, the pressure of them combined is going to be the sum of their individual pressures that they would create on their own. Just adding the pressures together. Possibly the easiest thing around. So if I give you an example question, you want to determine the total pressure, you've got the volume, you've got the temperature, you've got a mixture of a variety of things. If all you want is the total pressure, that's going to come from the total number of moles.
So this is only relevant during an ideal situation?
Right. So we are treating it as if it's an ideal gas. So you could treat this as a real gas. In that case, you would want to get the real pressure from the Van der Waals equation for the helium, and then add that to the real pressure from the Van der Waals equation from the hydrogen, and then also add it to the real pressure from the neon. So you have to solve the Van der Waals equation 3 times, because each time you solve it, you plug in different values for A and B, since each substance has its own values for A and B. You get all those pressures and add them together. So I'm not going to ask you to do that, because that's just overkill on the amount of time you spent doing math with the Van der Waals equation. So if I do give you a mixture, you can treat it ideally, and really that goes for any question, as long as I don't give some indication that it's deviating from ideal behavior, you can probably assume that it's behaving ideally. So here, if we want to know if it's behaving ideally, we can look at the conditions. We've got a pretty large volume. We have lower than room temperature, but it's not like extremely cold. And we have not a large number of moles, right? So those conditions don't suggest it should be deviating from ideal behavior very much. Because we need a very low temperature, or a very small volume, or a very large number of moles usually to cause ideal behavior deviation. Plus, the substances we're dealing with are all nonpolar, and they're all relatively small, so they shouldn't be creating a lot of polarizability or areas of partial charge to attract. So I wouldn't expect that to be deviating much from ideal behavior. So if I want the pressure, I'm going to get the pressure equal to nRT over V. So I need the total moles. And so that's going to be the moles of each gas added together, 0.0194 plus 0.0411 plus 0.169. And when I'm adding and subtracting sig figs, I look at how many decimal places of information I have. So in the first 2 numbers, I've got 4. I've got information out to the 4th decimal place. But in this number, I've only got information out to the 3rd decimal place. So when I add those together, I can only have confidence out to the 3rd decimal place. So I would add 0.0194 plus 0.0411 plus 0.169. That's going to give me 0.2295, but this one is not significant. So I want to keep that for now because I don't want to round until the end. But I have to keep in mind that that number really does have only 3 sig figs, so when I'm multiplying and dividing with it, my answer can't have more than 3 sig figs. So then I would plug things in here. I would plug that in for the total number of moles. I would multiply that by R. which is 0.08 to 06 liter atmospheres per mole Kelvin. Multiply it by the temperature, but I've got to convert the temperature to Kelvin. So I have to add 273.15 to the 15.8. So that's 288.95. And again, adding and subtracting. I only have information out to the first decimal place in that number. So again, this one is not going to be significant. Here I have 4 sig figs. So I don't want to round though until the end, so I'll plug that in as it is. Realizing though that I only have 4 sig figs with it. Then I'm going to divide by the volume, 2.50 liters. So I can include my units to make sure everything cancels out. And when I see everything canceling except the pressure unit, then I know that I don't need to do any extra conversions. Now, I'll probably make sure that you do that on the exam, because on the exam I might not give you the volume in liters. I might give it to you in milliliters. Or I might, not give you the pressure in atmospheres. I might give it to you in millimeters of mercury. So make sure this is the value for R that you're using. When you plug in the volume, it's got to be in liters. When you plug in the temperature, it's got to be in Kelvin. When you plug in the pressure, it's got to be in atmospheres. So then I can plug that into my calculator because all my undesired units cancel. And I get 2.18 atmospheres. Limited that to 3 sig figs because I had 3 sig figs here and 3 sig figs here. There's nothing with less than that, so that's my answer. Any questions about that? Let's look at 11.69 here. In this one, they ask us about air on the top of a mountain where the pressure is 0.8 atmospheres. So let's just assume they gave us an extra sig fig there, even though they didn't. So let's say we're talking about atmospheric pressure, and we want to know what the partial pressures are of the nitrogen and oxygen in the air. So how do we figure out that? So this is kind of similar to what we just talked about, but from the reverse perspective. Instead of using the partial pressures to get the total pressure, or the total moles to get the total pressure, we're given the total pressure and we want to work backwards to figure out what the individual pressures are. So we're looking for the pressure of the nitrogen and the pressure of the oxygen in the air on the top of the mountain where the total pressure is 0.8 atmospheres. What do I need to do for that? So I don't really know the individual pressure, so if I knew one of those, I could subtract from the total to get the other one. Yeah, so I do know that the partial pressure of the nitrogen plus the partial pressure of the oxygen will equal the total pressure. That's definitely true. Whatever they are, they have to add up to 0.8. But I need a little bit more information before I can really solve this. So the question tells me to see problem 11.55, where it tells me that 78% of air is nitrogen, and that 21% of the air is oxygen. Those are numbers I need. So that means out of 100 molecules, 78 of them are nitrogen and 21 of them are oxygen. So out of the total pressure created by those molecules, 78% or per 100 is going to be the nitrogen. So that's a fraction that I need to set up. So I can say 78% or per century or per 100 times the total is going to give me the nitrogen. The fraction of that 0.8 total that's the nitrogen is 78% or 78 per 100. So if I multiply that, I find that it's 0.62. If I want to check my work, I can easily do that. I take the 0.62 divided by the total, the part divided by the total, multiply it by 100, and make sure I get 78%. 78% of that 0.8 atmospheres is 0.62 atmospheres. That's the pressure that the nitrogen is causing. And so I would then do the same thing for the oxygen. 21% times the 0.8 total is going to give me 0.17 atmospheres. And that's the pressure due to the oxygen. Questions about that? So then just to point out, if you add up the pressure of the nitrogen and the pressure of the oxygen, you get 0.79, which is not quite the total pressure. Why is that? Yeah, it's because even though the air is like 98% nitrogen and oxygen, there's still other things, argon and other things. So the total pressure is going to be slightly higher than the individual pressures here because the two individual molecules we're looking at are not everything that's actually present in the air.